Well, here we go. This is the last video in General Chemistry 1. We are going to start by looking at the solid state of matter, and there's a couple things that we need to define, such as what is a crystalline solid. An ionic solid is a solid that is formed with alternating positive and negative charges together. We have a metallic solid, which we'll talk about, covalent network, molecular solid. All of these are different types of solids. Okay. When we talk about something that is crystalline, all that we mean is it has a repeating pattern to it. The opposite of that would be amorphous. Now, glass is an example of something that's amorphous. Now, when we look at properties, we think of it as a solid. But if we look at it on the molecular level, it does not have a repeating pattern. So it isn't not really fitting the definition of a solid. Okay, so looking at some things that do, silicon dioxide, SiO2, has a ratio of 1 silicon to 2 oxygens, but notice that it has the repeating pattern that happens here. Now, occasionally, we're going to get a fused silica if we cool it really fast, which doesn't quite have that same repeating pattern. When we take a look at sodium chloride, we have the positive and the negative charges that alternate with each other, and this is an example of an ionic solid. Copper is a metallic solid, and metals are interesting because they have a bunch of electrons. Now, like say for copper is going to have a valence electron, and the rest of it is considered a positive ion with a valence electron. And that electron isn't localized to one atom. It can go freely throughout the entire structure. We say it's delocalized, or that we have a bunch of positive ions in a sea of electrons. That's what gives metal its distinct properties. It's malleable and ductile. I can move one of the atoms just a little bit without breaking the bond. That's why they can bend without breaking. Okay. And here we see covalent network solids such as a diamond, silicon dioxide, silicon carbide, or graphite. Now, what's interesting is that in the graphite and carbon, we actually have alternating single and double bonds here. Its bond order is 1.5. In carbon, we have pure tetrahedron. Its bond order is 1. So the bonds in graphite are actually stronger than the bonds in carbon. But in graphite, we have sheets that just break off. And those sheets are only held together by intermolecular forces. That's why graphite is considered softer than a diamond. We also see molecular solids, such as carbon dioxide. Ice is another example. And they still have the same repeating crystal structure. Okay. Let's see. Here you see an example of something called allotropes. We have diamond and graphite. And diamond and graphite both are made of pure carbon, but they have different structures. We could actually have a phase diagram of solid carbon substances. Okay. Here you see types of crystal defects. You might see a vacancy, you might see an impurity, and sometimes those impurities are intentional. For example, if I have iron and I stick a carbon in every once in a while, it makes it much stronger. You might call it steel. Okay, that's an interstitial impurity that we see. We also have substitution, where we have an atom that is substituted and is not the same size as the whole. Some important things. The simplest repeating structure is called the unit cell. The points along the unit cell that are at the corners are called lattice points. And when metal atoms are arranged with spheres in one layer directly above the other, we call it a simple cubic. Basically, we have a simple cube. And notice that in this simple cube, take a look at this atom here. This atom is actually in 8 different cells. So each of the corners have 1/8 of the atom in that cell. Overall, there's 1 atom per unit cell for face-centered, for simple cubic. Here we get into something which is a simple cubic lattice, so we can see this. Now, notice that this is a coordination number of 6. Even though that atom is in 8 different cells, it's only attached to 6 other atoms. So the lattice points of a simple cubic, again, 8 corners, and the edge of a unit cell is 2 times the radius or the diameter. So we can find out something about the size of the atom from this, or we can find densities, quite a number of different things. You might find interesting problems on these. Okay, we also have something called a body-centered cubic, which is like a simple cubic, but in the center of that cube, there is one atom completely within the unit cell. We also have face-centered cubic, which on the face of each one, there is one atom that is shared with the adjacent unit cell. So each of the face-centered ones is in half of this one and half of that one. So when we count atoms, a simple cubic is going to have one atom. Now again, there's 8 atoms that have parts in there, but each is 1/8. So that's 1. Okay, the body-centered has the same 8 corners and the one in the middle. So it has 2 atoms per unit cell. In the face-centered, we have 3 atoms per unit cell, or 4 atoms per unit cell. Okay. Going through another way that we look at it, if you put balls as close together as possible, they don't end up in a straight cubic arrangement. They actually are shifted. So instead of having these in a square, what you would expect, we actually have them offset a little bit because they can fit closer together. This is called closest packing. And we have hexagonal closest packing and cubic closest packing. The difference is the layers that are 2 apart from each other. If they're directly above each other, we call it cubic closest packing. If they are not directly above each other, see, this one is above this little gap here, that is hexagonal closest packing. Okay. Another thing that we can pay attention to for a face-centered, the diagonal of the cube is 4R. We'll also look at body-centered here in a minute. A unit cell is defined by the length of its 3 axes, A, B, and C, and the angles alpha, beta, and gamma. Now, this is very important. This defines the type of unit cell that we have. Here you see 7 different lattice systems and 14 different unit cells. There's actually a lot more than that, but looking at it very simply, the cubic, we have simple cubic, face-centered cubic, and body-centered cubic. These are which all the sides are equal to each other and all the angles are 90 degrees. And then you can see we get less and less ordered as we go until we end up with something like rhombohedral or triclinic, which doesn't have any angles or sides equal to each other. Okay. Now, cations can occupy 2 types of holes, either octahedral holes or tetrahedral holes. And those are going to give different properties to the solid. Okay. Again, the body-centered, here is the face-centered. We have 2 radii that is across there. Body-centered, the diagonal is going to be 4 radii. Actually, 4 radius here. X-ray diffraction is one of the most important methods of determining the structure of a solid. What happens is that as the beam comes in, it is going to bounce off the atoms and is going to be reflected, and it's going to give an interference pattern. And by calculating back that interference pattern, we can determine the exact arrangement of the atoms. And even more than that, we can obtain very closely the identity of the atoms. Now, we might not be able to tell between 2 adjacent atoms, such as copper and zinc. Those may be a little bit beyond our ability to distinguish at this point in time, but we can figure out those by other means. But this is called X-ray diffraction. And many substances have been defined, their structure, by using X-ray diffraction. Okay, one of the most important ones was somebody by the name of Rosalind Franklin, who came up with the structure of something called deoxyribonucleic acid, DNA. Yes, Rosalind Franklin is the one who discovered the structure of DNA, not Watson and Crick, who actually came up with the Nobel Prize for it. Franklin was a inorganic chemist. She was a crystallographer. Okay, and with that, we have finished the course. You have one more exam followed by the final exam. I wish you good luck on everything. I hope you've learned a lot, and I hope you really enjoyed this class.